We'll start with the review of the Kalman filter equations, which I have written down on the board, and it's on this slide over here. Okay? We talked about Kalman filter is a special type of observer with a observer gain given by some equation over here, which is related to the disturbance stochastic properties of the disturbance. And then we talked about last time how to implement this Kalman filter law is to solve this Riccati equation to obtain this matrix M over here. The derivation of this Riccati equation is like this. You just plug in, let's see, plug in this equation to here. You're going to get mk plus 1 equals A. So it's going to be zk, which is mk minus mk c transpose. CMK, C transpose plus V inverse CMK. Then A transpose plus BW, WBW transpose. So if you simplify this equation, you're going to get what's written on this slide over here, the Riccati equation. Last time we talked about how this Riccati equation is going to converge under the controllability and the observability conditions. And then over there we compared, this is the essential message I want to talk about today. Over there we compared the situation of the stability result. We mentioned that the Kalman filter equation is going to be stable, even if the system itself is unstable. Okay? And I want you to be able to derive this result here. For example, if I want to derive the Kalman filter sort of closed loop dynamics. By this, I mean I want to be able to express, I will start with this case. I want to express this x hat k plus 1 given k to be some sort of expressions k given k minus 1 plus then some term here yk then plus some term here uk. Okay? So I want to, the explaining of this equation is like this. What do you think a standard observer looks like? A standard observer is it a single input, single output system or not? If you want to design an observer for a system. The observer is going to give you estimation of the states. What are the inputs for the observer? So an observer is not a single input, single output system. It's at least double input, single output. Actually, it's not even single output because the state sometimes is a vector. So an observer is usually a multiple input, multiple output system. So over here, this is why I written the equation this way. So the input for the Kalman filter dynamics are the signals u and y. Okay? And then the dynamics is trying to estimate the state, so it's x hat. I want to be able to derive from these equations here, these 4 equations here, to this equation. Okay? That's what I mean by Kalman filter dynamics. So detailedly, the mathematics looks like this. I have x hat k plus 1 given k equal to, I'm going to use this statement here, a x hat k given k plus b u k. And then I'm going to substitute this Kalman filter state dynamics over here to get a x hat k given k minus 1. So here I'm connecting the two state estimations at different time steps. plus f. This case, I'm gonna omit the index here for the F matrix. Then I'm gonna get yk minus c x hat k given k minus 1 plus buk plus buk. Okay? The reason why I omitted the index for the observer gain is that we have known that in the steady state, the observer gain is going to converge to a constant. So I'm actually doing the steady state, assuming steady state. Yeah, linear time invariant time. And then the Riccati equation has converged. Okay? So here, you see, the structure looks exactly like what I wrote down in the last slide. So it's going to be some term which is related to x hat k given k minus 1. So it's going to be a identity minus f c x hat k k minus 1 plus af yk plus buk. Okay? So this is, you see, something different here. It's not A matrix. It's not simply the A matrix. It contains something else. Okay? This is intuitive to understand because recall any kind of observer design or even LQ design. Any kind of observer design, let's say, equals AX hat K plus BUK plus L, I will use L in a standard observer. If you recall, 232 minus CX hat K. You see, recall in any kind of standard observer, the dynamics is going to be A minus LC X hat K plus something related to Y and then something related to U. So, you see, in any kind of standard observer, you have something similar. It's just in this case, the Kalman filter case, it's another type of A matrix here. So in a standard observer design, you have to make the eigenvalue of this matrix to be inside the unit circle. Now, think about it. When we design Kalman filter, we never mentioned how we never designed the Kalman filter based on the dynamics of this matrix. We sort of just started from the least square estimation, and we derived this. Now, the nice result is, if we do that, this matrix, guaranteed, stable. By stable, I mean the eigenvalues are inside the unit circle. So that's something nice, and I want you to be able to understand that. Okay? So, let me start here. Alternatively, this is one thing we can do. Alternatively, I'm going to start discussing an equivalent statement. The result is going to be equivalent. Alternatively, I can express this kind of dynamics into this form. X hat k given k plus something related to yk plus something related to uk. I can also do this. And the steps how to achieve this is exactly the same as this step. The result is going to be I minus FC A. Then here, I don't care about this for the moment, because I just want to show you that these matrices guaranteed eigenvalue inside the unit circle. Okay? That is, the derivations are here. Okay? So I have derived this state dynamics, Kalman filter dynamics, shown here. The first thing to notice when you see this is that these two matrices are different. And I have explained that the Kalman filter dynamics is going to be stable. So both of these matrices guaranteed eigenvalue inside the unit circle. Actually, if you dig into the details, the eigenvalues of A minus AF as C are exactly the same as eigenvalues of A minus Fs CA. Okay? There are multiple ways to understand this. So the simplified case, the special case. Special case is, let's assume A is non-singular. If you want to prove this eigenvalue statement, you gotta need to show that the determinant of, let's say the eigenvalues are lambda I minus A minus AFS C equal to the determinant of lambda I minus A minus Fs CA. Right? So one intuitive way to understand this is that if I start with lambda I minus, so look at the left-hand side here, lambda I minus A, so the inside is identity minus Fs C. If I multiply this equation with A on the right, if A is non-singular, all the matrices are square, so I can do this. Then I'm going to get lambda A minus AI minus Fs C A, which is equivalent to, now I can pull out an A matrix from the left-hand side to get A lambda I minus Fs C A. Everyone follows this? Okay, now take determinants on both sides. I'm going to get determinant lambda I minus A. So the inside of this is AI minus Fs C times determinant of A. So this side is exactly the left-hand side of this equation here. And the right-hand side, you got another determinant of A, and then times determinant of lambda I minus Fs C A, which is exactly the right-hand side of this equation here. So we started with the special case that A is non-singular, so these two are going to cancel. They are not 0. So this is one way to understand the result. The general case. So if A is singular, A can be singular. In this case, the determinant of A is 0. A singular means A has eigenvalues at 0. So this kind of analysis no longer holds. What we're going to need to do is to use another type of result. So I will mention this at the moment, but I won't prove it. It's a fact that the determinant of I plus m times n equals the determinant of I plus n times m, provided that the dimensions match. Okay? But either way, I just want you to understand this is our goal. And as long as you get this idea, it's fine. All right? Any questions for this part? When you say conditions, do you mean the controllability conditions? Those are sufficient conditions for the steady state Kalman filter to exist. yeah, it may not be that the Kalman filter gains is going to converge to a constant. It might be, yeah. Yeah, this is for the steady state Kalman filter. Mm. 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 Because that case is more complicated. If I have a time varying Kalman filter, the gain are time varying. The system is a time varying system. So stability of a time varying system is not as simple as this. It's more complicated. It doesn't mean that it's unstable. It just is beyond the scope of the. Generally, it's stable. Yeah. Mm. This case. So we started with my. Oh, here. So this is to clarify one thing, that we have derived the Kalman filter dynamics, these two equations. Both of them are Kalman filter dynamics. But the A matrix inside are different. So I just want to say that both these matrices have the same eigenvalues. So if one of them is stable, the other one is also stable. Yeah, that's the purpose. Okay. So this slide is not really that essential. The main idea is like we have explained, we have stated. I didn't prove this. I stated that this matrix, the eigenvalue of this matrix, are inside the unit circle, but I didn't prove it. If you think about what I did, so this is explaining why it's the stability holds in this case. So it's very similar to the LQ analysis. You just have to understand the main ideas here. The detailed steps are a little bit more evolved. So the main idea is this. Remember, we have the Riccati equation, ARE. Okay? Look at this ARE. You see that some terms inside are very familiar. And I'm looking at, for this purpose, I'm looking at this term. I'm going to use tilde here. What is this term here? Recall on the blackboard. This is the gain, right? The Kalman filter gain. And on this side, you see something also very similar. C times ms. If I have something on the left times C times ms, I can have another fs transpose. The idea is we have explained the Kalman filter closed loop dynamics is related to this matrix. So I wanted to show that the system defined by this closed loop matrix is stable. So I want to show, I want to have one type of Lyapunov analysis here, which is, if I can do, essentially is this one. Essentially is this one. So if I can somehow create this closed loop matrix A out of this Riccati equation, okay? If I can somehow achieve this, then you see we have shown that is this MS matrix positive definite? Two questions. Is this positive definite? Is the right-hand side at least positive semi-definite? What about the first one here? When we say the Kalman filter, the Riccati equation, when we say the two assumptions, controllability and observability, one of them is going to guarantee the Riccati equation is going to converge to a constant. what does the other condition guarantee? So MS, the other condition is going to guarantee MS is positive definite. And what about this side? This side is easier to see. First of all, it's symmetric, you see. What about this term here? Is it positive semi-definite? Negative of this? Semi-definite. It may not be completely negative definite. For example, you see W is positive definite. So let's say W is 1, 1. As an example, let's say BW, I'm going to let it be, let's say for simple case, 0, 1. Now, look at this. It's going to be, B should be a column vector. So it's BW is this. Then I'm going to have 0, 1 times 1, 0, 0, 1. And then on this side is 0, 1. Huh? BW? Oh, here. Let's see. Oh, yeah, I made a mistake. BW in this case should be scalar case. Yeah, let's say 1. I made a mistake there. Good catch. So, yeah, is this matrix positive definite or positive semi-definite? Positive definite? This is actually a little bit tricky. Positive definite, positive semi-definite are sometimes very tricky. So positive definite means for any matrix, I'm going to say positive definite means if I multiply this, if multiply x transpose on the left-hand side and x on the right-hand side, the result has to be positive regardless of any x, right? Now, what if x is, let's say, x is 1, 0? You see, the result is 0. So as a general fact, even if W is positive definite, if you have these things on left-hand side and right-hand side, it's going to mess up the positive definiteness. So the matrix on the right-hand side is not necessarily semi-definite, negative semi-definite, not negative definite, but it's at least negative semi-definite, okay? Anyway, that's a little bit review of these results. But the main message is this. It's exactly the same as the LQ problem. If I have A closed loop times M A closed loop transpose minus M equals negative Q, which is negative semi-definite, and this M is positive definite. You see, this is a Lyapunov equation. If I have this result, what does it say for the stability of the system? It's at least stable in the sense of Lyapunov. Okay? So this is exactly the main message in this slide. It turns out, after doing some manipulations, we can translate this algebraic Riccati equation to this Lyapunov-like equation. Over there, you can see the Kalman filter closed-loop matrix A, the equivalent closed-loop matrix A matrix in Kalman filter. In steady state Kalman filter is this guy. So the conclusion is that this Kalman filter dynamics is at least stable in the sense of Lyapunov. That's the main message here. Okay. So after the additional analysis, it's able to show that actually the system is strictly stable, asymptotically stable. But that's, again, take it as much as you can. But if you kind of feel lost over here, it's fine. The main message is Kalman filter is good. It's stable. Okay? Now, starting from this slide, it's going to be a little bit involved. It's going to require some background knowledge of ME233. In ME233, when we discussed the LQ problem, I'm pretty sure you remember this symmetric root locus analysis and the return difference equation over there. So in the Kalman filter, it turns out the analysis is quite similar. There's also a return difference equality in Kalman filter, and there's also a symmetric root locus in Kalman filter. So, okay, it's going to be, as I said, it's going to be a little bit evolved, and it's maybe a little bit dry, so stay with me on this. We have the Kalman filter dynamics over here. The first equation over here, okay? If I do a Z transform of this guy here, then on the left-hand side, it's going to relate it to Z x hat kk. Okay? Then I can move this term on the left-hand side here. And these terms doesn't change. You see, fsy, I minus fsbuk, and then this fsca x hat kk. So this Kalman filter equation can be equivalently represented by this block diagram. Actually, this is the reason why I have been keeping saying Kalman filter, closed loop Kalman filter, because this equation has some kind of closed loop dynamics, can be represented in this closed loop dynamics. Okay, so how this guy comes from here, you see, is exactly. Let me start it with. Here, I have, okay, I can start here. I have the x hat k given k signal here. If I pass this signal to CA signal, this is the signal CA x hat k given k. Then I have on this side negative fs times this signal here. And then to complete this block diagram, I'm going to need this term to occur, fs times yk plus 1. Then another term, which is, let me put it here, which is I minus fsc times buk plus. Then here, you see, I have expressed this signal as the summation of these two plus the summation of these three terms. So this signal, let me denote it as Q, let's say, Q signal. Denote this as Q signal, maybe QK. So you see, QK and X hat, K given K, is related by X hat, K given K. It equals Zi minus A inverse QK. So I have explained how to go. That's why this Zi minus A inverse here. So you see exactly this guy is equivalent to this block diagram shown over here. So there is some type of closed loop dynamics inside the Kalman filter. Now, as I mentioned, there is a return difference equality in Kalman filter. First of all, I want to start by reviewing how does anyone know how this return difference, what does return difference mean? In this block diagram. So if you haven't seen this before, return difference is defined by this. If I, can I borrow a pen? The pen. If I inject a signal identity here, if I inject the signal identity here, then I'm going to have passing through this path. The signal here is going to be Fs Zi minus A inverse Ca. If I inject the signal here, if I inject the identity signal here, passing through this path, I'm going to get Fs Zi minus A Ca. This is signal here. Okay? So this signal got returned. This is the returned signal if I have a constant injection here. Return difference means the difference between the signal I injected and the signal that's returned. The signal that's returned, keep in mind there's a minus sign here. There's going to be minus Ca Zi minus A inverse Fs, which equals this. Okay? So the return difference equality, if you see what does return difference mean, then it helps you to understand the return difference equality. It's expressing some kind of properties this return difference has to satisfy. Okay? And the derivations are a little bit too much to do in the class. So I suggest you to take a look at the ME232 reader if you want to know the details. But, yes? Here? Mm-hmm. Oh, this? So the student asked why this is injected. This is going back to the first equation here. Why these two block diagrams? Why this block diagram is equivalent to this? So let's go back a little bit here. I have on the left-hand side yk plus 1. So this guy is going to give me this term here. So I want to be able to express x hat k given k as the summation of these terms here, right? So this guy is going to give me this, right? This guy is from here. Yeah, there's no additional term. Yeah, so after I added this one, these two are equivalent. Okay? So if that is cleared, let me come back to this return difference equality equation here. So I explained, it's telling us how the return difference, this is the return difference, how the return difference, what kind of properties is satisfied. It turns out it's this. So this is from the algebraic Riccati equation. You can get this return difference equality. Let me give some additional information here. So the way, if you recall the way we learned about this return difference, you see, return difference is something related to it's some closed loop. This is just the intuition. Closed loop, if I say, explains the closed loop dynamics. Right? It's the difference between the injected signal and the return signal in this closed loop system. And on the right-hand side, what do you see on the right-hand side here? G is defined by Gz equals C A is the open loop dynamics here. C A Z I minus A inverse Fs. G is defined by this. So what does the right-hand side here intuitively looks like? So the right-hand side, you see, is telling us something about open loop. I will use the term transfer function. Everyone sees that? The right-hand side is something related to the open loop transfer function here. The return difference, you see, is telling us how the closed loop dynamics and the open loop transfer function are connected. Nothing else. So take this message, which will be the only term that we're going to be using for the following slides. Okay? And the detail, you see, it's has kind of symmetric structures here. This is because the Riccati equation has some kind of symmetric structures. But nothing else, nothing more fancy here. Let's do one additional intuition here. If I have an open loop system closed by this negative feedback, and this G. So I'm giving the intuition of this return difference equality in the simplified case of a single input, single output system. Let's say BZ, AZ. Here. So what do you think are the closed loop dynamics? What determines the closed loop pulse in this case? Closed loop pulse in this feedback loop. 1 plus GZ, right? So the closed loop poles are determined by BZ plus AZ, this closed loop characteristic polynomial. Okay? So you see, it's exactly the case. The closed loop dynamics it can be expressed as something related to the open loop transfer function. You see, if I divide it by AZ here, I get 1 plus BZ divided by AZ, which is GZ. So this is the same intuition here. In the return difference equality, I have something about the closed loop dynamics. And on the right-hand side, I have the transfer function. So nothing more. It's just telling us how the closed dynamics are related to the transfer function here. Okay? Now, if I want to know the closed loop eigenvalues, what should I do from this return difference equality? Here is just a bunch of matrix multiplications. How will I be able to obtain the closed loop eigenvalues out of this? So take the determinant of this guy, I can obtain the closed loop eigenvalues, right? That's actually the same, if you recall 232, that's exactly the same how we obtain the symmetric root locus by taking the determinant of the return difference equation. Yes, that's a very good question. That's exactly what I'm going to show now. So I'm going to show you that if you take the determinant on the left-hand side, the closed-loop eigenvalue is just going to come right out of it. Okay? So here, if you take the determinant of this return difference, this is the return difference. Okay? Let's do the math together. Take the determinant of this guy here. Determinant of I plus CA. I'm going to denote this big matrix as temporarily as M. Okay? Can you see that this determinant equals M times CA? Can you see that? I have stated this fact before, that determinant of I plus N times M equals determinant of I plus Mn. All right? So now you see, take this as the matrix N here, then you see they are equal. All right? How many of you want to see the proof of this? At least half the, if half of you guys wanted to see the proof, I will do the proof. Otherwise, I will send a reference to you after class. So how many of you want to see the proof? Let's see. Not enough. So I'll send you a reference how to prove this after class. So at the moment, just believe me, it's the truth. All right? So now you see. Now you see why this is happening. So the determinant of I plus CA times this, you see, if I shift, I can change orders. I can put this on the left-hand side of this to get this. All right? And over here, look at this guy. This guy equals determinant of, I'm going to pull out Zi minus A here, inverse here. And then inside I have Zi minus A in order to create this identity, and then plus FSCA here. Now because it's a product between these two, it equals determinant of Zi minus A inverse times the determinant of Zi minus A plus FSCA. So which is this case here. So because determinant of the inverse matrix, it equals 1 divided by the determinant of this matrix. Okay? So look at this guy. Let's start with the easy case here. What does this guy give us? This is it will give us the open loop eigenvalues, because it's calculating the eigenvalues of the A matrix here. What about this guy here? It equals, inside is Zi minus A minus FSCA. Okay? It's giving us the eigenvalues of this matrix. And if you go several slides earlier, this is the Kalman filter closed loop A matrix. Okay? So immediately you see the result. Here. Immediately you see, if I take the determinant on the left-hand side, I'm going to get if I take, you see here, take the determinant on the left-hand side. I'm going to get, for the first term, I'm going to get beta z divided by phi of z. And then inside here is the determinant of v plus cms c transpose. Over here, this is be a little bit more careful about this term here. What will this, take the determinant of this guy, what will it do? What result will come out? In the form of phi and beta. Determinant of this guy. Be careful. It's z here, but it's z minus 1 here. Which term here? Yeah, so be careful about this here. If you take the determinant, it's going to give you this. And then on the right-hand side is determinant of v plus gz w gz inverse transpose. Okay? So I can shift terms. No, I can remove this. I can shift terms. I can put these terms, the denominator, to the right-hand side, and I can divide both sides by this determinant to achieve this result here. Okay? So let's do the special case here, which is related to symmetric root locus. What if G, let's see, what if GZ looks like a wide transfer function matrix? Then this term is going to become a scalar. If it's a wide matrix, the transpose is going to be a skinny matrix. So this is going to become a scalar. The determinant of a scalar is itself. Okay? And then if GZ has this kind of form, that means y, yeah, let me ask you a question as a test. If GZ is a wide matrix, what's the dimension of the output and what's the dimension of the input? Let's say this is a 3 by 1 matrix, transfer function matrix. 1 by 3. 1 by 3. 1 by 3. What are the dimensions of the input and output? Y should be a single output, so it's 1. And I should have 3 input. Okay? So if this happens, this is going one step further. If y equals cx plus v, now you see, if y is single output, then v has to be a scalar, right? So if that happens, recall what's the definition of v? V is the covariance matrix of the noise. So if v is a scalar, it's a scalar random variable, then you see this is going to be a scalar. So the result is going to be just to take out the determinant parts. So it's exactly showing here. So I can take out the determinant terms to achieve this. So I can pull out v and then divide by v here. This is given us, if I assign this as 0, this is so here, more exactly. Here. If I want to know how the closed loop poles look like, this is defining the closed loop poles, closed loop eigenvalues. See here. So the closed loop eigenvalues, if I want to see how that looks like, I can simply, by assigning this to be 0. Right? Now, what will happen if, let's say, what will happen if W divided by V, if this term is approaching 0. So this is, we're moving to symmetric root locus. What will happen for intuition? This is also a review. What will happen if I have K, G, in a closed loop system? What will happen if K is approximately 0? What are the closed loop poles for this system? That's the first question. Second question is, if the system are stable, what will happen if K is approaching infinity? What will be the closed loop poles of this closed loop system? This is the root locus analysis. It's a review. If K, let's do the first case. If K approaches 0, what are the closed loop poles? No, there's still pole. Open loop poles, right? If this is approximately 0, then it's essentially I don't have the feedback. I cut off the feedback closed loop that connection. Then it's the poles are the open loop poles. Then if K is going to infinity, then the poles are the open loop zeros. Okay? So exactly the same thing here. If this term approaches 0, then the poles defined by this are the open loop poles of this transfer function here. And then here, if it approaches infinity, then the common filter poles are going to be the zeros of this matrix here. Okay? There's just one thing that you need to pay some special attention to, is this. If the poles of GZ are, all of them are stable, if poles of GZ are stable, how will the poles of GZ minus 1 look like? Stable or unstable? And why? Yeah, it's kind of easy to see. If GZ is Z minus, let's say, 0.8, 1. Take a simple case, you can see. If GZ looks like this, then GZ minus 1 looks like 1 divided by Z negative 1, negative minus 0.8. The zeros of the poles of this guy is going to be 1 divided by 0.8. So if the poles of these are stable, then the poles of these are unstable. This is exactly why it's called symmetric root locus. Because there's always one pair, another pole that is directly related to, there's always an unstable pole that's directly related to the stable pole. Okay? Now if you buy that, let's see the result here. Pay special attention to this. Okay? I said common filter poles has to go to the stable poles of this guy. And in the case of the W divided by V goes to infinity, it goes to the stable zeros of this. Why is that? Why I can say it will go to the stable poles and zeros? That's a thing that you have to pay attention to. Yeah, so even if this guy has unstable poles, unstable zeros, but the common filter poles will not go to the unstable one. It has to be the stable poles of that. Why is that? Yeah, exactly. That's exactly the reason. We have proved that the common filter is stable. right? So it will it will not be the unstable poles of this. That's something very subtle. So look at here. These are the poles, right? This is given the Kalman filter pole. This is given something different. It's the mirror of the Kalman filter pole. So what I'm saying is the Kalman filter poles from here is going to go to the stable ones, and the poles here are going to go to the unstable ones. That's a hidden message. Anyway, that's something very subtle. Yeah? Mm-hmm. Yeah, yeah, yeah. Eigenvalue is 1, okay? Mm-hmm. Marginally stable. That will count to. Let's first see. So your statement is that GZ has a marginally stable pole. Okay. Then you are asking how the Kalman filter pole is going to look like. So one thing to notice here is that these are the limiting cases. So it says it's going to approach the pole, regardless of whether I treat it as stable or unstable. It says it's going to approach this pole. It's never 1, it's approaching 1. So it's still stable. So it's going to approach from somewhere. Let's say if this is 1, the Kalman filter pole is going to do this. It's going to approach to this, but it's still inside the unit circle. Yeah, in that sense, in the limiting sense. And there will be some pole that's going from this side. Yeah. Okay? But keep in mind, guys, the main message is Kalman filter is stable. And we can have tools to analyze the stability and how the poles is going to look like. Okay? Now, I want to switch gears to the continuous time case. And I won't, unlike the discrete time Kalman filter, I won't derive everything here. I will just describe the central equations and the result here. So the continuous time case, the system is going to look like this. Again, W and V, they are white Gaussian noises. Okay? And in this case, I'm assuming the initial state. So the assumptions are the initial state is random, and then W is random vector, V is random vector. Okay? And again, we are trying to minimize xt with its estimation given all the measurements from 0 to t. Okay? And the equation for the continuous time Kalman filter is going to look quite similar to the continuous time observer dynamics. So it's going to be the derivative of the estimate equals ax hat plus bu plus f times the error term. Okay? And then the Kalman filter matrix, gain matrix, is going to be given, is again related to the statistic properties of the noise and m, which m additionally depends on w. So the gain depends on the property, stochastic properties of the noise. Okay? And if we have the observability and controllability assumption, I am going to have the Kalman filter is going to have a steady state Kalman filter, where the gain matrix are constant and the covariance matrix is going to be also converged to a constant value. So this is very, again, we can have the duality with LQ problems where we have the algebraic Riccati equation here. And this looks very similar to the algebraic Riccati equation of the Kalman filter. Okay? Mm-hmm. Where? It means x hat t slash t means the estimation of xt given y tau, where this tau is going from 0 to t. This is what it means. Okay? It's using all the information up to t to estimate x of t. Okay? Now, there's one thing that's really fantastic about Kalman filter. It's think about what we have done. We have derived the Kalman filter equation, and then we have discussed what the Kalman filter is trying to do. It's trying to do optimal state estimation under noise case. We have not discussed how well Kalman filter is doing. Okay, we have not discussed, for instance, in this case, we have not discussed how this residual term is going to look like. We have not discussed whether this residual term is truly something we cannot do, we cannot minimize any further. Right? I have not discussed this guy. If somehow I can show this error term is just impossible for us to reduce further, then that's saying the Kalman filter is doing a great job. Everyone sees that? So this is what I want to do next. I want to show you that this residual term is just a Kalman filter already gives us the best thing we can achieve. This residual term is impossible to reduce it further. That's what I want to do next. Okay? So I just need two statements, two observations to be able to achieve this. First of all, for the Kalman filter equation, again, I can obtain how the Kalman filter equation looks like in a block diagram, which is shown here, which is very similar to what we have seen in discrete time case. We again have x hat and fs times this error term, y minus this c times x hat. And then if I want to be more rigorous, again, I will have to put bu t here. But this is the closed-loop dynamics, closed-loop block diagram for the Kalman filter equation. Okay? Now, we have discussed the discrete time Kalman filter problem has a return difference equality. For the continuous time case, it also has a return difference equality, where this term, again, you see, is the difference between if I inject a signal I here, and then the returning signal is going to be C Si minus A inverse Fs. Okay? So the difference between the signal I injected and the signal that's returned is the return difference I plus C Si minus A inverse Fs. Okay? So there's also return difference equality. Now, I can simply substitute S, every S, with j omega to achieve this equation here. Okay? Someone tell me what is the transfer function from y to ey? What's the transfer function from y to ey in this block diagram? So it's a multiple input, multiple output transfer function. So it's going to be just as a review. For a single input, single output case, what's the transfer function between y and ey? It's going to be 1 divided by 1 plus g, right? It's the actually it's called if you have taken any loop shaping class, it's called the sensitivity function. It's called the sensitivity function of the closed loop system. So for the multiple input, multiple output case, scenes are exactly the same. The transfer function from y to ey is going to be now it's going to be some inverse term. Inverse of I plus the open loop transfer function, which is going to be C Si minus A inverse Fs. Okay? So the sensitivity function is defined by this guy here, which is, as you can see, it's the inverse of the return difference. That's again giving us the confirmation that the return difference is telling us the closed loop information. Okay? All right. So now you have seen, this is what we have derived. The transfer function from y to ey is the inverse of the return difference here. If you see that, if I know the spectral density of y, what will be the spectral density of the ey signal here? What will be the spectral density of ey here? Okay, that's the question. So this is talked about, I think, 1 week ago maybe. If the input going to a system G, the output, then the spectral density of the output is going to be G, let me do the continuous time case, G j omega, G negative j omega times the spectral density of U, the single input, single output case, all right? So for this case, this is just the matrix case, all right? This is the multiple input, multiple output matrix, and these are the inputs. So you're going to see that the system dynamics is going to appear twice. So this guy is going to appear twice. The result is this, okay? So if you know the spectral density of y, then the spectral density of ey can be very simply obtained by this result here. This is G y to E y, j omega. This is a G y to E y, negative j omega, and then transpose. All right. So negative. Yeah, should be negative. Yeah, it's a typo. According to the laws I announced earlier, homework 2, come to me in my office hour. I'll give you the hint for one of the homework problem. All right? So yeah, it's negative. It's typo here. Okay? Now, if I have the system dynamics that looks like this, what will be what will be the spectral density? Because I have sort of see that I need this quantity. So what will be the spectral density of this given the system dynamics like this? The result is going to be, I have, it looks like this. W going into my system, which I have denoted the transfer function as G. Again, I have a typo here, but I found it out. This is another typo. So if the picture is this. If I have W going into the system, then this is how the picture that looks like. It's V here. This is Y, all right? So W is the noise term. And then V is the other noise term. Okay. I haven't put this U term here because it's a deterministic signal. So it won't affect the stochastic properties of the system. All right. So from here, you will be able to understand this equation here. Okay. If I denote this as Y1, now you see the spectral density of Y1 is going to be G, J, omega, if this is G. Let's say if this is G. G, J, omega. Then W, which is the covariance matrix of W. G negative J omega transpose. All right? And then Y, the spectral density of Y is just going to be the spectral density of Y1 plus the spectral density of V, which is give us the equation here. Okay? That's how the spectral density of Y looks like. Okay? Now, look at this return difference equality. Look at this return difference equality. On the right-hand side, I have a spectral density of Y. And on the left-hand side, I have these results here. And I have shown you this. I've shown you that the spectral density of EY is this times this times this. So look at the equations very carefully. If I multiply the inverse of this matrix on the left-hand side, I'm going to get, and then multiply the inverse matrix of this guy on the right-hand side, I'm going to get exactly V equals I plus Cj omega I minus A inverse Fs inverse phi yy. Then here is I plus C. I won't write it the full result, but this is this guy here, right? Now look at these results. Look at this one and this one. The right-hand side are exactly the same. So it gives us a conclusion that the spectral density of EY, the arrow signal, equals to V. Okay? That's from these two observations. All right? So the right-hand side equals exactly the right-hand side here. So give us this conclusion. What does this tell us? The arrow signal, the spectral density of the arrow signal is flat. Right? This is saying it's independent of omega. It's going to be constant at any frequencies. What does that mean? It's white, right? It says EY is white. Okay? So if you think about it, white noise is, we cannot do any further if we have white noise. So this is the best we can do. The Kalman filter has achieved the best result that it can achieve. The estimation error is white. Okay? So that's good result. That's saying Kalman filter is doing a great job. Yes? make it to V over 2. No, because it's kind of, that's a good question. But let me go to here. So this is the noise term in the output, way here. Okay, that's just the noise over there. If I have a sensor that's giving me this error, I can do nothing about the sensor, right? So the Kalman filter result is giving us the spectral density EY is V. It's giving us the best thing it can do. The sensor, we cannot change the sensor noise, right? It's given to us, right? So, yeah, think about it. It's the best we can do, right? Now, okay, so I'm just going to finish up with quickly with telling you that for the continuous time Kalman filter, there's also a symmetric root locus, which is by taking the determinant, very similar to what we have done in the discrete time case, which is taking the determinant of the return difference equality and obtaining this result here. Okay, so for a single output case, it's again, we can analyze what will happen if V divided by W approaches 0, and what will happen if it approaches infinity. Okay, the result is going to be exactly the same. Okay, so if V divided by W goes to 0, then the Kalman filter poles is going to be the stable poles of the transfer function here. Okay, if it's going to infinity, it's going to be the stable zeros of this transfer function. Let's see. Okay, I had wanted to do one example for the symmetric root locus. I don't have time, but it's provided in the course reader. So, and it's very easy to read. You can take a look at how the root locus simple case will look like. Okay, so wrap it up. We have finished the following topics. We have defined the big picture of Kalman filter problems, which is least square state estimation. And then we discussed the discrete time Kalman filter, continuous time Kalman filter. Over there, we have, this is deriving the Kalman filter equation. And then here is basically showing Kalman filter has good properties. All right? So that's the end of Kalman filter lectures. In the next lecture, I will discuss how Kalman filter can be used in feedback control design. Okay. See you next time.